Hello and welcome to my video lesson 3.5 on Lenz's law. Similar to the last video where we could push electrons through a wire to create an electromagnet, which in turn interacts with the magnetic field, that's where we made a motor. We can also reverse this effect by moving the magnetic field around the conductor, which creates the electron flow in the conductor. That's inducing an electron flow. So this is a generator. So this is the reverse of an electric motor. And actually, essentially, you can just spin an electric motor by hand. And as long as it has a permanent magnet, which most of them do, it will actually generate electricity. A motor and a generator are basically the same thing, except for the fact one has a battery that's on and pushing electrons through. One is, if you are hand spinning it, you will generate electricity on the other end. Pretty cool. So how does this actually work? Well, you can see here, I've got a diagram and we've got electron flow. So we can see that the electrons are flowing this way right now. And it's not always easy to tell, but it looks like those electrons are going this way, because it looks like it's coming down and, through here. Okay, and then it goes down, and then it comes back this way, up, across, down, 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 and down. So hopefully you can kind of see the electron path all the way through. Okay, it says, given the image below, which way is the wire spinning inside the magnetic field given the result of its electron flow? So we see the electron flow. It's going this way. Now unfortunately it does reverse and flip every time, but let's consider the position where, it's not super clear, but let's consider the position where it's going in and around like this in the magnetic field. So there's a north here and a south below. As it is, it's not. No, actually, it should work just fine. Okay, so what we're going to do is we're going to use our hand rule. So this will just be our third hand rule. So I'm going to just show you guys below. So we're going to be using this hand rule here in order to solve this question. So the thumb is the electron flow, the fingertips are the magnetic field, and the palm is the force, the push. So if you look at, this spot right here, and you zoom in, you can see that the electrons are going into the page. Okay, and there's north above them and south below them. And then if you zoom in, I'll maybe use a different color, zoom in right here, they're coming out of the page with north above and south below. So in those two positions, what's going on? Well, first of all, we have, maybe I'll just use a different color so we can see it very more clearly. But we have magnetic fields going down from north to south like that. So those are where my fingers are going to point. Maybe I'll just put that here. Fingers. Okay, so that's where my fingers are pointing. The X means that my thumb is going into the page, and the dot means the thumb is coming out of the page. So we're going to do one at a time. We're going to do the red one. Now, for the red one, if it's going into the page and the fingers are pointing down, that means my palm is pointing in this direction. So palm, which means it's the force. Okay, and maybe I'll just label this here. The red one means my thumb is into page, because that's the direction of electron flow. Okay, and same thing in green. but this time my thumb is out of the page. But also electron flow. So this time my thumb is going out of the page, which means that my force is reversing. So again, this is the force here. And this is coming from my palm. So in that position, that means it's being pushed this way and pushed this way. So which way is the wire spinning? Well, it's being spun clockwise. Now, it must, so that's, sorry, I've said something wrong. It's generating electrons. So this is what it would be if it was a motor. So everything I've done is based off the last video. This is what it would be if it was a motor. Now the problem is that if this is what the forces are looking like, then it's happy moving this direction. Now, what actually is happening when you have a generation happening? Generation means that we're creating electricity. Electricity can't just happen out of nothing. Electricity comes from some other energy. We're changing from one energy form to another. So in the case of a generator, an electric generator, we're changing from kinetic energy to electric energy. So how is that really happening? Well, it's a very similar process to how friction turns kinetic energy to heat energy. Friction is always opposing motion and always fighting against whatever direction you're moving. This works the same way. So if it's spinning to the right, then if it's spinning clockwise, then the forces are actually in the wrong direction. Right? Because then the forces are not opposing the motion. Well, we're generating electricity here, so the forces actually have to reverse. So this must be counterclockwise. So actually, to change this, to make it actually correct, we're going to flip everything. So what we're doing now, I'm going to just erase all this, is we're actually going to show it flipped. And now it's counterclockwise. So let me explain what this means. Okay, now we're going to put our fingers, we're not going to put our fingers any way at all. Okay, what we're going to do is just label the north and south of the magnet. But we're going to look at where the force is pointing. And we're going to look at where the electrons are flowing. The electrons are flowing into the page. And the force is going down on the red one. Which means that at the top, it's going to be, it's going to be kind of fighting against the motion. So it needs to, as it's going towards the north, it's going to be repelling north. And then as it's going to south, it's going to be repelling south. And then once it gets past, it's going to actually reverse this. And this is going to make more sense in some of the next ones. But essentially, it's the reverse of what a motor is. So everything we did was a motor, but you have to keep in mind that it flips because it is fighting against motion. So we can use all the different hand rules depending on the occasion for these types of questions. So when you're generating electricity using a moving magnet and or moving wire, you can use the hand rules, but you have to be careful because you need the hand rules to oppose the motion. So let's take a look at these examples. So example number 1. Okay, determine the direction the wire must be forced in order to induce electrons to flow towards point A. So we're now assuming that electrons are flowing upwards. Okay, now if it's flowing upwards, that's the direction I'm pointing my thumb. And the magnetic field right now is pointing to the right. Now, if I would normally do this, if you're just thinking, what would happen to let's say this was not a wire. Okay, let's say it was a negatively charged particle. What would happen to the wire, to the negatively charged particle? Well, it would be pushed out of the page. But that's not what we're doing here. What we're doing is we're forcing the wire to be moved. So we're actually reversing what is natural. And we're pointing our wire's magnetic field lines in the opposite direction. So our fingers are pointing this way with the electron flow this way, which means that my force is into the page. And I'm pushing it that way. That's the direction I'm pushing the wire, because the force that's going to be pushing against me is actually going to flip that. So the velocity of the wire is into the page. That's the way I'm pushing it physically, me, not the magnetic field. The magnetic field is pushing against me. It's always pushing against motion. Okay, let's continue, and let's try two other questions here that are just slightly different. We're trying to oppose motion, right? So here we've got a coil of wire, and we know that if a magnet is going to come towards it, it's opposing motion. Well, how do we know it's opposing motion? Well, or how do we make it oppose motion? Well, if we have a north end of the magnet here, and we have a north end of the coil of wire there, then they will oppose motion. And this is where it starts to become a little bit more clear, in my opinion. So when you have this, you're going to use the second hand rule. So just by the way, it looks like that. Okay, this is what we're working with right now. Okay, so we've got the second hand rule. Okay, and we're pointing our thumb in the direction of the north. Okay, so it's, I don't know, our thumb is pointing this way, to the right. Okay, now with our thumb pointing that way, that's how we make sure that it's fighting against the motion of the magnet. But our fingers are the electron flow. So if you look at the top of your knuckles, they're all pointing this way, which means, you know, you follow that back or you follow it forward, depending on which one you want to do. And you can see that the electron flow is from right to left. Okay, let's take a look at the next one here. Now, here the motion of the magnet, well, it's on this side, and it's opposing motion. The magnet is being pulled away from the coil of wire. So it must be attracted, actually, to the coil of wire, because that is what would pull the magnet this way and oppose the motion. So the north is on that side, and the south is on this side. Well, actually, that's the same as what we had before. So our hand stays in the same position, and it's the same direction of the electron flow from right to left. And this is interesting because you can see there's a few different ways of flipping this. So we have the motion of the magnet. We've got the magnet poles themselves. Motion of the magnet and the magnet poles. Now, if we flip both of those at the same time, then nothing actually changes in the wire. So, yeah, kind of an interesting combination of things. All right. I hope this video helped you better understand Lenz's law and the idea of electric generation and the forces that are caused with moving magnets or moving wires next to each other. I hope this video helped, and good luck.